Welcome. Today we will be exploring dynamic programming, an interesting type of algorithms with a wide range of applications in the real world. So before I go on to explain the details and how exactly this algorithm functions, there's some glossary terms that we should go through. So the first one, the one that I consider the most important for dynamic programming, is memoization. Not memorization, it is without the I, without the R. Memoization is the process of storing solutions to previous subproblems instead of recomputing them every time. That is a critical process in dynamic programming and an important technique in computer science. Recursion, also a very important concept to dynamic programming, refers to a specific type of methods that refers and uses itself within the implementation of the method. Subproblems, as mentioned in the concept of memoization, these subproblems are subtasks or smaller tasks that are part of a greater problem or task that the programmer is trying to resolve. Tower of Hanoi, that's a very classic mathematical puzzle. The easiest solution is implemented through recursive programming, and I'll be explaining more about that as we get onto the applications of the algorithm. Sequence alignment, also a concept at this time in biology, implemented through dynamic programming, and I'll be getting to those as we get into the applications section. So an interesting saying about dynamic programming is that those who do not remember the past are condemned to repeat it, referring to the process of memoization and storing solutions to subproblems that are already solved instead of resolving them every time. The algorithm. So what is dynamic programming? It is a technique in programming for solving a complex problem by breaking it down into a collection of simpler subproblems. So instead of tackling the whole piece at the same time with brute force, you're still solving the problem with brute force, but this time you're solving easier subproblems that can be tackled with relatively shorter code or techniques. Each subproblem is solved and their values are stored, and ideally in a proper data structure, to be referred back to and extracted when needed, which is the process of memoization. Recursive programming, as demonstrated on this diagram on the right, is an aspect of dynamic programming, since it implements the solution of previous subproblems that are less complicated, and it combines these solutions to find the final answer, and that reflects the principle of dynamic programming. So some important applications and implementation of this algorithm. It is very important to recognize that dynamic programming itself is dedicated towards the purpose of optimization. It is still brute force. The methods developed through dynamic programming still uses quite a bit of brute force, but it's the idea of reducing the amount of brute force that are used as compared to tackling the whole problem at the same time. So in bioinformatics, it lies in sequence alignment. Sequence alignment, that's a very complicated process in today's biological studies, comparing the similarities and differences between the genetic information of different organisms, which are usually millions of sequences and nucleotides. These are very, very long strings to compare, and a method, an algorithm called global alignment algorithm, breaks these long sequences of DNA down into shorter sequences of ATCG of the nucleotide sequence, and you can compare these sequences separately and then combine the answers of the alignment together to find the final alignment solution to a whole set of DNA. And that is definitely dynamic programming. Protein folding and structure prediction, also in bioinformatics, uses a similar approach, breaking down into smaller structures and identify those instead of solving the whole problem altogether. In mathematics, the most important application I would say lies in matrix chain multiplication. If you have a series of matrices, they can be multiplied together in a variety of different ways. However, all these different ways of calculating this matrix chain multiplication has different costs, which is the amount of calculations it takes to achieve the purpose. Different costs may vary greatly, as demonstrated in this diagram on the bottom right. You can see that the amount of calculations are very, very different. If we can locate the least amount of calculations it takes to perform this multiplication, we'll save so much more time in this calculation, and that's what dynamic programming does with matrix chain multiplication, and it'll solve the problem in the end by breaking it down again into sub-problems. In economics, dynamic programming is applied to optimal consumption and saving. At a certain time, if we're trying to decide if a person should save, how much he should save and how much he should spend, we're looking at the whole spending and saving history of the person, which are all sub-problems that have been solved before and hopefully stored in proper data structures. So instead of looking at this point in time with so much more complex information from the past, we've solved all these sub-problems from the past, allowing us to solve the bigger problem more easily at the end. That also applies the concept of dynamic programming. So one example I decided to take on is the classic problem of Tower of Hanoi. As you will see in these two diagrams on the left, in these two pictures on the left, the problem is very simple. There's 3 pegs and a bunch of discs. So the purpose is to move all the discs, which are in largest to smallest ascending order, move all the discs from peg number 1 to peg number 3 in the exact same order as they appeared before. So as you can see, that could be a little bit of a complicated problem, since we're trying to find the least number of steps it takes to solve this problem. It becomes a mathematical puzzle. And the solution of a 4-disc situation is demonstrated in this animation below. Interestingly, the Tower of Hanoi problem can be simply implemented with the recursive relationship, in which when you're trying to move n number of discs from peg H to peg T, what you're really doing is moving n-1 number of discs from peg H to the peg that's not H or T, the middle peg, and then you're moving the largest piece, as you see in this animation, largest piece from H to T, and then again you're moving n-1 discs from the middle peg to the final peg T. In that process, recursive programming can be implemented as I did with my solve method, which is below. On the right here, we can see that in the else statement, I implemented 2 recursive implementations of solve, and exactly using the relationship we found with Tower of Hanoi. And I use object-oriented programming, so I created the problem as a class. I create an object of this class, implement the solve method, and here I'm solving the 4-piece solution again. And using my move method, I actually have shown on the console the exact steps it takes to achieve the final solution, which pegs, which discs to move. For some reason, it has given me 3 solution statements saying solved in steps. I've yet to find out what exactly the problem is, but for all our intents and purposes, this doesn't influence the final solution to the problem, and I think I've completed most of the implementation of dynamic programming here. So recursive programming is a way to implement dynamic programming, but it is not the only way, as we'll see in our second example with the triangle count the white contest problem. So this problem is relatively more complicated with a more advanced implementation of dynamic programming. So the question is, given a grid of data, as you can see below here on the 5 sample input box over here, it is clear that there's a bunch of triangles in there as defined by these shapes up here. These are all called triangles. Even a singular hashtag is called a triangle. It is inputted as a file. I'm supposed to output the amount of triangle in each of these grids. So that becomes a little bit more complicated of a problem. Instead of just looking at implementing a recursive programming idea, you must manually break down the problem into sub-problems first. So I noticed that one of the biggest issues with the problem is that I don't know how long the longest continuous sequence of hashtags is. So I first write a longest method, which in itself is also recursive. Allows me to search through the entire grid, which have been inputted into a grid of 2D array of chars. I'll be able to search through and find the longest and store the longest length as an integer. So then I write another method, which is also very interesting. So I notice that well, if you want to find out how many triangles there are, you must make sure that the things you find are triangles. So I wrote this try method, implement the 3 parameters: int length, which is the base length that you're looking for, the bottom left indices, which int r and int c represents. This method is also recursive, looking at how different levels of the triangles, confirming that they all match the shape I want. And the last method I've implemented in this triangle count problem, as we'll see in my code and my next videos, is the trick method, the TIRC method, with only one parameter, L, which is the longest length within this triangle grid system. It counts the triangles. It is also recursive. I'll get into details of this in my later videos. So as you can see, dynamic programming not only implements recursion, it also depends on the programmer's idea of what are the subproblems that must be solved before we go on to the bigger problem. Obviously, I could have written all of this in the same method, which definitely would have been very, very complicated. See all this longest trick and try all these methods. By writing them separately, I have a clearer line of logic, and I'm able to solve this problem more easily than if I were to write it together. And that is all about dynamic programming. I'll go on and explain and show some of my code and implementations of it in the next videos. And thank you very much for watching this. And by the way, here are some of the references and important sources I use to solve my problems. Thank you.